Now, example 6.11. Suppose the loop in exercise 6.4 is stationary, but the current feeding the electromagnet that produces the magnetic field is gradually reduced so that the field decreases from the initial value of 0.3 Tesla at the rate of 0.02 Tesla per second. If the cut is joined and the loop has the resistance of 1.6 ohm, how much power is dissipated by the loop as heat? What is the source of this power? Okay. Now see, here the loop that we have to consider, which one is given to you in example 6.4, it implies that length and breadth for that particular rectangular loop, that is 8 centimeter and 2 centimeter. So length is 8 into 10 raised to minus 2 meter, breadth that is 2 into 10 raised to minus 2 meter. Magnetic field that is 0.3 Tesla, and the rate of change that is 0.02 Tesla per second. Resistance of the loop that is 1.6 ohm. Now we know this thing, EMF induced due to change in flux, that is d phi by dt. So we can write d by dt into A dot B. Phi that is A into B. Now A, area is constant. Therefore we can write A dB by dt. And now substitute area that is length into breadth. So 8 into 2, 16, and 10 raised to minus 2 into 10 raised to minus 2, that is 10 raised to minus 4. And rate of change of field that is given to you 0.02. You will get the answer, EMF induced. Now the current constituted in the loop, that is E by R, resistance of the loop that is given to you 1.6 ohm. Now power dissipated in the form of heat, that is I square R, whatever is the answer of I, substitute in this bracket, R that is given to you. And what is the source of this particular power? So source of power, that is changing magnetic field. Okay. Then example 6.12. A square loop of side 12 centimeter with its sides parallel to x and y axis is moved with a velocity of 8 centimeter per second in the positive x direction in an environment containing a magnetic field in the positive z direction. The field is neither uniform in space nor constant in time. એટલે with position અને time બંને સાથે change થાય છે field. એ ટાઈપનું field આપ્યું છે. It has a gradient of 10 raised to minus 3 Tesla per centimeter. એટલે position wise 10 raised to minus 3 Tesla per centimeter. This is the rate of change. And along the negative x direction, that it is increases by 10 raised to minus 3 Tesla per centimeter as one move in the negative x direction. And it is decreasing in time at the rate of 10 raised to minus 3 Tesla per second. Okay. So rate of change of field with respect to time, that is 10 raised to minus 3 Tesla per second. Determine the direction and magnitude of the induced current in the loop in its, if its resistance is 4.5 milliohm. Now here, see, suppose we consider when the motion of the loop takes place at the time, due to its different positions only, the field is changing. EMF will be generated. Okay. So that EMF we have to calculate. But in addition to that, during its motion with time, the field is also changing. So due to change in field with respect to time, what is the EMF induced in it? That also we have to calculate. And then after, the net field induced, net EMF induced, that we can write E1 plus E2. So independently we have to calculate the EMF induced due to rate of change of a field with respect to position and time, and then after we have to take the summation of these two. Clear? So this one is the concept. Area is given to you 0.12 meter whole square, because the side that is 0.12 meter. V 8 into 10 raised to minus 2 meter per second. Now dB by dx, that is 10 raised to minus 3 Tesla per centimeter. Convert this centimeter into meter, so we can write 10 raised to minus 1 Tesla per meter. Now dB by dt, that is given to you 10 raised to minus 3 Tesla per second, and resistance 4.5 milliohm. So milli means 4.5 into 10 raised to minus 3 ohm. Now EMF induced, that is given by d phi by dt. Phi, that is A into B. A is constant, so we can write A dB by dt. A, that is 0.12 square. dB by dt is 10 raised to minus 3. You will get E1. Now this one is the EMF induced due to change in field with respect to time. Now E2, again we can write A dB by dt. But now here we have to calculate this EMF induced, that is due to change in field with respect to position, means X. So here rewrite this equation like this: A, now divide and multiply by dx, so we can write dB by dx into dx by dt. So A, but dx by dt, that is called speed. So A into V into dB by dx. Now area 0.12 square, speed that is given to you here 8 into 10 raised to minus 2, dB by dx, that is 10 raised to minus 1. So we will get the EMF induced. So net EMF induced, that is E1 plus E2, and this much volt. So current constituted, that is E by R, and R that is given to you, E is calculated here, you will get the answer. Clear to all of you, or any doubt in this? 6.13. It is desired to measure the magnitude of field between the poles of a powerful loudspeaker magnet. A small flat search coil of area 2 centimeter square with 25 closely wound turns is positioned normal to the field direction, and then quickly snatched out of the field region. Equivalently, one can give it a quick 90 turns to bring its plane parallel to the field direction. The total charge flown in the coil, measured by the ballistic galvanometer connected to the coil, is 7.5 millicoulomb. The combined resistance of the coil and galvanometer is 0.5 ohm. Estimate the field strength of magnet. Very simple example. See, area that is 2 centimeter square, so that is 2 into 10 raised to minus 4 meter square. The number of turns in the coil, that is 25. When it is snatched out of the field region, the charge flow, that is 7.5 millicoulomb, so that is 7.5 into 10 raised to minus 3 coulomb. Resistance that is given to you 0.5 ohm. So delta Q equal to delta phi by R. We already discussed this equation in theory. Now delta phi, flux, that is NBA, and say this Q, delta Q, that is Q. So now we want to calculate field. So make B as a subject of equation B, that is RQ upon NA. Your answer. Simple thing. Then after 6.14. Figure 6.20 shows a metal rod PQ resting on the smooth rails AB and positions between the poles of the permanent magnet. The rails of rod and the magnetic field are in three mutual perpendicular directions. A galvanometer G connects the rails through a switch K. Length of the rod is 15 centimeter and field that is of 0.5 Tesla. Resistance of the closed loop containing the rod is 9 milliohm. Assume the field to be uniform. Now, question A. Suppose K is open and the rod is moved with speed of 12 centimeter per second in the direction shown. Give the polarity and magnitude of the induced EMF. Now see first question. Length is 15 centimeters, so 0.15 meter. B, that is 0.5 Tesla. It is moved with a speed 12 meter per second, 12 centimeter per second, so that is 12 into 10 raised to minus 2 meter per second. Resistance, that is 9 milliohm, so that is 9 into 10 raised to minus 3 ohm. So when it is moved, this one is the simple case of motional EMF. So EMF induced in the rod, that is BVL. Substitute the value of B, V and L, you will get the answer. Now when rod is moving in the direction as shown in the figure, then each and every charge residing in the rod is also moving in the same direction. Field that is downward. It implies that now see, this one is the field in downward direction, this is the velocity, okay, that is in this direction, and your rod that is like this. So now each and every charge is moving in this particular direction. So as per equation of force on the charge moving in magnetic field B with velocity V, that is Q into V cross B. So this is V, this is B. So if you rotate right-handed screw from V to B, so like this, then the force on charge Q, that will be towards you. Now this is your rod. So on this particular rod, if we think about the direction towards you, so there the end of the rod is termed as P. So charge Q will experience the force towards P. So negative charge will experience the force towards Q. It implies that P end that will be positive and Q end that will be negative. Then after B question. Is there an excess charge built up at the ends of the rods when K is open? What if K is closed? So first question no answer, I'll say yes, because we already discussed this thing in A. The positive and negative charges experience the force in the direction of P and Q respectively. So these charges are accumulated. It implies that we can say excess charge built up at the ends. If what happens if K is closed? If K is closed, then the closed loop will be formed and this charge will flow and will constitute the current. Now with K open and the rod moving uniformly, there is no net force on the electrons in the rod PQ even though they do. So if they do experience magnetic force due to the motion of the rod, explain. Now if they are not experiencing any net force, it implies that the electric force and magnetic force both are perfectly balanced. Then and then only this one happens, right? It is experiencing magnetic force and net force is zero, means the force due to electric field and force due to magnetic field are perfectly balanced. So net is zero. Then after D, what is the retarding force on the rod when K is closed? So retarding force, that is F equal to BIL. We already studied in theory, when any current element IL is in the magnetic field B, the force on it, that is BIL sine theta. But here IL and B are perpendicular to each other, so simply we can write BIL. But I, that is E by R, E we calculated in question A, and R, that is given to you, length is given to you, B is given to you. So substitute values, you will get answer. Now, due to this retarding force, its motion will be opposed. If you want to sustain the motion, then you have to do mechanical work. It implies that mechanical power that should be supplied. Now, on that concept, the next question: how much power is required by an external agent to keep the rod moving at the same speed when K is closed? How much power is required when K is open? So, required power, that is force into velocity. Clear? So, force into velocity, force we calculated, velocity is given to you, you will get the answer. And same is required because Lenz's law is always present whether the key is closed or open. Okay. Then after, how much power is dissipated at heat is as heat in the closed circuit? What is the source of this power? So power dissipated as heat, that is I square R. So I, that is E by R. So simply you can write that is E square by R also. E we calculated, R is given to you. Substitute, you will get answer. And what is the source of this power? So source of this power, that is external agency which provide the mechanical power. That mechanical power is converted into electrical power, and that electrical power is dissipated in the form of heat. Then after, G equation. What is the induced EMF in the moving rod if the magnetic field is parallel to the rails instead of being perpendicular? So if field is parallel to the rod, then the EMF induced, that will be equal to 0. Clear? चलो समझ पड़ेगी बताइए. Then example 6.15. An air-cooled solenoid with length 30 centimeter, area of cross section 25 centimeter, and number of turns 500 carries a current of 2.5 ampere. The current is suddenly switched off in a brief time of 10 raised to minus 3 seconds. How much is the average back EMF induced across the ends of the open switch in the circuit? Ignore the variation in magnetic field near the ends of the solenoid. Now see, length of the solenoid, that is given to you 30 centimeter, that is 0.3 meter. Area of cross section, that is 25 centimeter square, so that is 25 into 10 raised to minus 4 meter square. Number of turns given to you, that is 500. Now current changes from 2.5 ampere to 0 ampere within the time interval of 10 raised to minus 3 seconds. Now back EMF. So in the theory of self induction, we studied this thing, the back EMF, that is minus L delta I by delta T. So minus L delta I, that is I2 minus I1 upon delta T. So we can write E, that is equal to, now I2 is 0 and this minus minus plus, so simply we can write E, that is L I1 by delta T. See, you have I1, you have delta T, but there is no information related to L, the self inductance. But in theory, we derived the equation for the self-inductance, and that is mu 0 n square A by L, where small n, that is the number of turns per unit length of the solenoid. Number of turns per unit length, that is total number of turns divided by total length. It implies that now mu 0 small n is replaced by capital N by small l, means that is the length of the solenoid whole square. Area as it is length I1 upon delta T. So here L square, in numerator L is there, so 1 L will be cancelled. So mu 0 n square A I1 upon L delta T. Now mu 0 4 pi into 10 raised to minus 7, total number of turns 500 square of it. Area, that is 25 into 10 raised to minus 4. Current I1, that is 2.5. Length, that is 0.3. And time, that is 10 raised to minus 3. And you will get the answer. Clear to all of you? Any doubt in this one? Then after 6.16. Obtain an expression for the mutual inductance between a long straight wire and square loop of side A as shown in figure 6.21. Now assume that the straight wire carries a current of 50 ampere and the loop is moved to the right with constant velocity V equal to 10 meter per second. Calculate the induced EMF in the loop at the instant when X is 0.2 meter. Take A equal to 0.1 meter and assume that the loop has a large resistance. Okay. Now see. First of all, we have to calculate the mutual inductance of a system of this long wire and this square loop. Okay. Now, as per definition, the mutual inductance, that is the flux associated with the loop per unit current passed through the another coil. અહીંયા આપણે લીધું છે long wire. So if we pass the current I through this long wire, then due to that particular current, the magnetic field will be produced in the surrounding of it, and now we can say some magnetic flux will be associated with the square coil. So now, first of all, we have to calculate that flux. Okay. Now see, magnetic field produced by long current carrying wire, that is mu 0 I upon 2 pi r, at a point which one is at perpendicular distance r from the wire. This we already studied in chapter number 4. Now here directly we can't write the flux associated with this particular square loop, that is B into area of the loop, because on this particular loop, starting from this side to this side, the field is not constant one. Field is continuously changing because for the points from this end to this end, the perpendicular distance from the wire is changing. So first consider infinitesimal thin strip in this particular loop having width equal to dr, length of this strip, that will be A itself because loop is with sides A. So flux associated with this particular thin strip, that is B into dA, area of this strip into magnetic field. Now this strip is at distance r from the wire. So magnetic field is given by mu 0 I upon 2 pi r. And area of this particular strip, that is length into breadth, so A into dr. So simply we can write mu 0 Ia upon 2 pi r dr. Now if we consider this square loop is made by this type of large number of infinitesimal thin strips. Now these thin strips will start from distance x from the wire to other end of the loop. So that will be at a distance x plus a from the wire. It implies that the position of the strips are changing from x to x plus a. So to calculate the total flux passing through this particular square loop, we have to integrate this particular equation of d5 between the limits x to x plus a. So 5 equal to integration x to x plus a d5. That is, now in this equation mu 0 I a upon 2 pi constant. So integration x plus a 1 by r dr. So mu 0 Ia upon 2 pi, now the integration of 1 upon r, that is ln r, limits are x and x plus a. So if we substitute these limits, then we can write mu 0 Ia upon 2 pi into bracket ln x plus a upper limit minus ln x the lower limit. So 5, that is mu 0 Ia upon 2 pi ln x plus a upon x. Mu 0 a 2 pi ln this x upon x is 1 and a by x. So ln 1 plus a by x and I is written here. So now if we compare this equation with phi equal to mi, then multiple of I, that is mutual inductance. So we can write here the equation for the mutual inductance for a system of long wire and square loop, that is mu 0 a upon 2 pi ln 1 plus a by x. Now say here mutual inductance is now calculated. Now if your loop is moving with velocity v, okay, then we have to calculate the EMF induced, because if this loop is moving with velocity v, then the flux associated with it will change. Okay, now E, that is minus d phi by dt. So here multiply and divide by dx. So we can write minus d phi by dx into dx by dt. Because here in the equation of phi, time is not appearing, but x is appearing here. See. But dx by dt, that is velocity v. So minus v d by dt. Then substitute here equation of phi. So phi, that is mu 0 Ia upon 2 pi ln 1 plus a by x. So minus mu 0 Ia upon 2 pi constant. Now differentiation of ln 1 plus a by x, that is 1 upon this one. Integration of 1 upon r, that is ln r. So differentiation of ln r, that is 1 upon r, like that. So differentiation is 1 upon 1 plus a by x. But we have to differentiate this bracketed term also, because inside it x is also there. So differentiation of 1 is 0. But differentiation of a by x, that is minus a upon x square. So this minus minus will be plus mu 0 I a into a, that is a square upon 2 pi into v upon, now this x square is taken in this bracket. So 1 into x square, that is x square, a upon x into x square, 1x will be cancelled. So plus ax. So mu 0 upon 2 pi I a square v here, x is taken common, so x into x plus a. Now mu 0 upon 2 pi, that directly we can write 2 into 10 raised to minus 7. Then current, that is given to you 50 ampere. Yes, 50 ampere. Okay. Then speed with which it is moving, that is 10 meter per second. Then a square. So a, that we have to take 0.1, 0.1 square. X, that is also given to you 0.2 meter into zero point 0.2 plus 0.0, 0.1. Now solve this one. You will get the EMF induced. Clear to all of you?